In this tab, we're comparing how easy it is to get an A in two professors' courses. So in Professor Caitlin's class, grades are distributed normally with a mean of 70 and a standard deviation of 15. Professor Chase's class, grades are distributed normally with a mean of 84 and a standard deviation of 5. If you want to achieve at least an A grade, which is set at 93 in both classes, compare the difficulty of obtaining this grade in both classes. In both classes, it is possible to earn more than 100. Considering the grade distributions, in which professor's class is it easier to achieve an A grade? Hint, the individual is an A. All right, so the individual is an A. The case is we want 93 or more, so the case is looking right. The mean in Professor Caitlin's class is 70. Standard deviation is 15. And Professor Chase's class, individual is also an A. Case is right. The mean is 84. Standard deviation is 5. And the grade we're trying to achieve in both places is a 93. Okay. So, just think about it. I mean, if you only had the mean, you would think, oh, well, I'll take Professor Chase, whose mean is much higher. But the standard deviations are really quite different, and that might change that result. So let's go ahead and calculate the z-score. So Professor Caitlin equals x minus the mean divided by standard deviation. Chase equals x minus the mean divided by the standard deviation. And then the probability is looking right. So let's go ahead and bring up our equations. So we need this one, probability looking right, 1 minus norm dot s dot dist. Oh, need an equal sign. Same here, equals 1 minus Okay, so if we look at the results here, you can see that there's actually a higher probability of getting a 93 or more in Professor Caitlin's class than there is in Professor Chase's class, which again is odd, because remember, Professor Chase has the 84 as the mean. Professor Caitlin has 70, but notice that it goes up faster. It goes 70 to 85 to 100, 2 standard deviations, whereas here it's 84 to 89 to only 94 at 2 standard deviations. So that's why. All right. So in which classes are higher probability of earning an A? That's going to be Professor Caitlin. And make sure you spell it just like it is over here. Which class has the higher standard deviation? In fact, you can even just go equals Caitlin like that. Which class has the higher standard deviation? Higher standard deviation is also Professor Caitlin. And true or false, standard deviation measures the average distance from the mean. That is true. Okay, in Professor Caitlin's class, what grade puts a student in the 50th percentile? So 50th percentile is a 70. And Professor Chase's class, 50th percentile is an 84. What's the percentile difference between the two? So that's going to be equal to That's 6.3 minus 3.6. And now, at what grade does Professor Chase match Professor Caitlin's percentile? So here's Professor Caitlin's percentile. And remember, since z-scores have a direct relationship to percentiles, we're going to look at the z-score. So we're going to say equals the z-score times the standard deviation for Professor Chase plus the mean for Chase. And now going the other way, at what grade does Professor Caitlin match Professor Chase? So we'll start out with the standard deviation for Chase times, the z-score for Chase times the standard deviation of Caitlin plus the mean of Caitlin. And we're good to go. All right, another one down. All right, on this one, we're looking at det percentiles. So Kaylee, and look and check out the spelling, because it's C-A-I-L-E-I-G-H. So be careful when you're spelling it later. So Kaylee's credit card debt is normally distributed with a mean of 5,000, a standard deviation of 1,000. Her debt is 1,500 below the average. So who's in a better position in terms of their respective debts? So better position is going to be basically lower percentile. So this is going to be looking left. So Kaylee's got credit card debt. Case is left. Mean is 5,000. Standard deviation is 1,000. And she's 1,500 below average, so she's at 3,500. Okay, Josh. Also looking left. Mean of 30,000. Standard deviation of 5,000. He's 4,000 below average, so he's at 26,000. All right. Just looking at this, it looks like Kaylee's in a better position, right? Because lower percentile. But let's finish it up. So the z-score is equal to x minus the mean divided by the standard deviation minus mean divided by standard deviation, and then the probability, we'll bring up our equations. Probability is equal to norm dot s dot dist z true equals norm dot s dot dist z true. Okay. So Kaylee's in the 6.7 percentile, and Josh is in the 21st percentile. So Kaylee's in a much better position. All right, in terms of percentile, who's in a better position? It's Kaylee. Actually, I'm just going to reference the cell so I don't mess up the spelling. It's Kaylee. Who's dollars owed, who's in a better position? That's still Kaylee. Which type of debt has the larger standard deviation? That's Josh. Which type of debt was the credit student loan debt? Sorry, so it's that one there, student loan debt. Okay. All right, now the empirical rule. What dollar amount would Josh need to reach to be in the 84th percentile. So 84th percentile, Josh is 35,000. What dollar amount would Kaylee need to reach for 84th percentile? That would be 6,000. What's the percentile difference between Kaylee and Josh? So we want a positive number, so we'll take Josh minus Kaylee. And what does Kaylee match Josh's percentile? Okay, so Josh's percentile translates to Josh's z-score. So we take his z-score times Kaylee's standard deviation plus Kaylee's mu. This would be 4,200. So that's how much she would owe for this red bar to come up here and match this one. And at what debt does Josh match Kaylee's? So it's Kaylee's z-score times Josh's standard deviation plus Josh's mu. Kapow! And we're done. Okay, so that last one, what it means for Josh to match Kaylee's percentile, in other words, Josh would have to be, that black line would come down here if Josh only owed 22,000 instead of 26,000. All right, and our last problem. So here we're studying the Amazon tree height. Now Libby is studying the heights of a rare species of tree in the Amazon, which are normally distributed with a mean of 100 and standard deviation of 15. She wants to find a tree in the top 1%. How high does the tree need to be to qualify? So this is different than every other problem that we've done so far in this unit, because now we're going to be using the equations on this side, because we're given the probability that we want, and then we're trying to calculate the x value that we want. So the case is right, because we want top 1%, so we're looking to the right. Mu is 100, standard deviation is 15. X is what we're trying to find, so we'll skip that. And we do have P of X, because we want the top 1%. So we can work backwards to a z-score. Now, to get the z-score now, we're looking right, it's norm.s.inverse 1 minus P of X. .33, and then to get x, it's going to be z times the standard deviation plus mu. So that's equal to the z times the standard deviation. So that gives us how much we're going to add to the mu. 135. So 135 is the magic number you have to clear to be in the top 1%. So how high does a tree have to be in the top 1%? It's going to be that 135. And what's the z-score at that number? Equals that. How high okay, now just using the empirical rule, how high does a tree need to be in the top 50%? Top 50% is 100. And how high does a tree need to be in the top 16%? So top 16 would be 115. Zap. And we're done. Okay. So it's pretty amazing stuff, because it all comes down to the normal distribution and the empirical rule. And some calculations that we can do using these formulas here. You should obviously try to memorize these formulas if you can, but if not, remember you can always bring them up on the screen. And we will see you next time.